Welcome to the world of radioactive decay and radioactivity. If we look at radioactive decay, so here's an example of cobalt-60, which is a radioactive material, and if we plot it versus time, we see that over time the concentration or the amount of material decreases, and it decreases in an exponential way. And so as this, for example, starts at, say, 10 grams, it decreases slowly as it goes down, and this is an exponential decay. And so we can see that this actually, radioactive decay follows first order kinetics. Remember first order kinetics? We could write our rate constant, our rate law, which would say that rate is equal to a rate constant multiplied by the concentration of A. So in this particular case, A would be cobalt-60. And this is a first order rate expression from our world of kinetics. And radioactivity is first order. And so what we were also able to do when we talked about first order reactions, we could say that the concentration of A at time t was equal to the concentration of A initial, or at time 0, and then multiplied by a factor which was e to the minus k, the rate constant, times time, or how much time had been elapsed. And when we looked at integration, we could integrate. We would say that the natural log of A at time t divided by the concentration of A at time 0 was equal to minus kt. And so we had these three expressions that we often talked about during kinetics. And we also said that when the concentration at time t was one half that of the initial concentration, the time was known as the half-life. And in radioactivity, it's all exactly the same thing. So here this was called half-life, which was natural log of 2 divided by k. Where did this come from? We used this expression here. We plugged in this value of AT as 1 half of A0 in here, and that gave us the natural log of 2 equals minus KT. We rearranged it. Now, radioactive decay, instead of using the symbol K for a rate constant, it uses a different decay constant, but it's exactly the same thing. And this lambda value here is the decay constant, and it's the same as the rate constant. And instead of using concentration, radioactivity, when we talk about radioactive decay, we use the number of nuclei, and we call this big N. So instead of using concentration, we use the number of nuclei, big N. And so here we have our equations that we talked about in first order kinetics, and here we have the same ones in radioactive decay. And so hopefully you can see that they're exactly the same. So here rate equals K times the concentration of A, decay rate is equal to lambda, which is the same as K, times the number of particles, or the number of nuclei. And then if we go and we look at the integration of these, we can also say that at time t, it's related, the number of particles or the number of nuclei at time t is equal to the number of initial nuclei multiplied by e to the minus lambda t, same as this expression. We can also see that if we wanted to look at the relationship between these, we could see that the natural log of the number of particles at time t divided by the number of particles or nuclei at time 0 is equal to minus lambda t, exactly the same as this expression. And we talked about half-life. Well, guess what? Here's half-life for a first order reaction. Here is half-life for a first order reaction when we're talking about radioactive decay. Natural log of 2 divided by lambda, same as natural log of 2 divided by k, because lambda and k are pretty much identical. And so important thing to realise is that n of t is the number of nuclei or the moles remaining at time t. N0 is the initial number of nuclei or moles. Same way as we talked about when we talked about kinetics. And so realistically, these are the three equations that you need to know to be able to do all types of radioactive decay problems or questions. And these three expressions, 1, 2, 3, are all exactly the same as the ones from kinetics. And so if you want to do any of the problems that come along with radioactive decay, you're going to use one or more of these three equations. And so what we'll do is we'll have a look at a couple of questions. So let's look at a typical question. This question in particular says radon 222 has a half-life of 3.823 days. And the question asks, how long will it take a sample of radon 222 with a mass of 0.750 grams to decay into other elements, leaving only 0.100 grams of radon 222? And so the way I like to do these questions is I realistically want to write down, well, what do I know? Well, I know the half-life, T half, because it's given to us here. I know that N0, the number of nuclei or the activity at the initial time, was 0.750 grams. Here it is. And then we're also told that we're left with 0.10 grams. So after a certain amount of time, NT equals 0.100. And so what we need to do is we need to find T. And so if it looks to me that we have these three equations here, and it seems like we really need to know lambda. Why? Because in order for us to find T, we're going to use either this expression or this expression. And in order to use these two expressions, we need to know the value of lambda. And the way we can calculate lambda is from this equation here, because we are given the half-life, and natural log of 2 rather miraculously occurs in a calculator. So the first thing we can do is we can use this equation for half-life, which is natural log of 2 divided by lambda. We can rearrange it, multiply both sides by lambda. We get lambda equals natural log of 2 divided by the half-life, natural log of 2 divided by 3.823 days, which were given in the question. And so this tells us that lambda, the decay constant, is 0.1813 per days, or days to the -1. And so now we have this value. We can take this value and we can use it to calculate the rest of the question. So we're going to use this expression here, which we know is one of our three equations. We want to know the value of time. We now have a new value of delta. We're told in the question what NT is and N0. And because of this, we can now rearrange this equation. So what I'm going to do is divide both sides by -1 over lambda. And so time now is -1 over lambda, natural log of NT over N0. We're given NT in the question. We're given NO in the question. We just calculated lambda. We put them all together in our fine and dandy calculator. And what we end up with is T equals 11.1 days, because of course this was in days. So the answer is 11.1 days, and this of course is to three significant figures, because when we look at the lowest number here, this is three significant figures. So it takes 11.1 days for radon 222 to go from 0.75 grams to 0.1 grams. And so that's just using those equations. And so we could ask another question here. So in April 1986, there was a large explosion at a Russian nuclear power plant in Chernobyl, also an HBO movie series. And one of the largest isotopes that was removed was cesium-137. Actually ended up in Wales and England, and affected some of the sheep when I was a younger person. And so the half-life of cesium-137 is 30.17 years. And so we could ask the question, if a 4-gram piece of cesium-137 was ejected from from the explosion at Chernobyl, how many grams would be present today in 2020 after this had decayed? And the answer should be in 3 significant figures. And so what we can do is, well, we look at the equations that we've got, and we realise that this equation here would be a great equation, because what we're actually looking for is we want to know how many grams or how many particles or how many moles or of material left at time t, and we're given N0, we're given that as 4 grams. We know that the time here is going to be between 1986 and 2020. What we would really need to know is we need to know lambda. So we can calculate time. Currently 2020 minus 1986 gives us 34 years. We know that N0 is 4 grams. So we would use this expression here, but we need to know lambda. And so in order to know lambda, we can calculate lambda from using this expression over here for half-life. And again, if we multiply both sides by lambda and divide by half-life, we end up with lambda equals the natural log of 2 divided by half-life. So lambda is log of 2. Natural log of 2 divided by 30.17 years. We're given this in the question, and we end up with a decay constant of 2.297 times 10 to the minus 2 years to the minus 1. So we have this lambda value, which we can now insert and use in this equation over here. And so we know NT, which is what we're looking for, is going to equal N0, which is 4 grams. And as long as we keep this in grams and this in grams, the expression is going to work. E to the minus lambda t, we now know lambda, which we calculated over here, multiplied by time, which is 34 years. We use a calculator, and we end up with N at time t is 1.83 grams. So what this says is that a 4-gram piece of cesium that was ejected by Chernobyl would now weigh 1.83 grams and would still be highly radioactive. And so the last style of question where we could be asked some other expression of, well, what about a fraction of material that's left? So if we look at a nuclear waste product with a half-life of 24,000 years, we're asked what fraction of this material will be present in 1,000 years. And so what we're given is the T of the half-life is 24,000 years. We're told that the time that we're looking for is 1,000 years, the value of T, and what we're asked for is what fraction is left. And so this is the fraction that's left. It's the amount of material at time t divided by the initial material. So this is the fraction that we're looking for. And so again, we'll go back to these 3 equations, and we look at these 3 equations, and so often we end up using this equation, the half-life, to calculate the decay constant. That's exactly what we're going to do here again. Same version. We end up with natural log of 2 divided by the half-life. We end up with a decay constant that's 2.9 times 10 to the minus 5 years to the minus 1. And then we use that to calculate the value that we're most interested in, which is this expression here, which is the ratio of how much material is left relative to the amount of material that was there at the beginning. And so this we can rearrange this expression, divide both sides by N0, and we end up with this expression. We know the value of T, which is 1,000 years. We know the value of lambda because we just calculated it. We put these numbers in the expression. We multiply it through. We end up with a value of NT over N0 is 0.97. And what this says as a percentage, it says that 97%, because we would multiply this number by 100 to get percentages, 97% of this material is left after 1,000 years. I mean, that's pretty incredible. that after 1,000 years, 97% of this material, highly radioactive material, is still going to be left. And so by using these three equations here, we can really answer any question that's related to radioactive decay.